Hello Pre-Calc PC. Today we are going to be talking about something called mathematical induction, and mathematical induction is a method for proving that statements involving natural numbers are true for all natural numbers. And in order to prove statements using this principle, we need to satisfy two conditions. So the first condition we need to prove true is that the statement is true for all, or for the natural number 1, which means we're just going to use a 1 for n. And also, if the statement is true for some natural number k, then it is also true for the next natural number k plus 1. Basically what this does is, imagine if you have a bunch of dominoes, and we are able to prove that you knock down the first domino. That would be the natural number 1. And let's say you are also able to show that somewhere farther down the line, a domino and the domino after it, k and k plus 1, also fall down. Then what we can assume is that all of the dominoes in between these are also going to fall down as well. Okay, so we are going to show that this statement is true for all natural numbers. So the very first thing we are going to do is we are going to let n equal 1. And all that means is that we're just dealing with your first term right here, which is 1, and we are setting it equal to this guy right here. Okay, you can also just say that n is 1 here. Either way, you're going to have 1 equal 2, plug in a 1 over here, and that's 1 times 2 over 2, which is still equal to 1. So yes, 1 is equal to 1. This is confirmed, and now we can go on to statement 2. All right, so statement 2 is going to be a little more complicated. The first thing you're going to write is you're going to let n equal to k, and in order to do that, we are just going to plug a k into this whole expression right here. So we have 1 plus 2 plus 3 plus dot 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 plus k is equal to k plus 1 over 2. Okay, again, we're just replacing the n with the k. Now we are going to prove true for k plus 1. All right, so this is the big part here. We're going to prove that this also is true for k plus 1 as well. So let's look at what that would look like. All of these, or this expression here, just has 1 plus 2 plus 3. It's going on and on and on. Plus our k value, plus k plus 1 is just going to be the value right after that. Okay? And all you're going to do, which we have done before, is on this side, instead of a k, we're going to plug in a k plus 1. All right, so k becomes k plus 1. The other k becomes k plus 1 plus 1. I know you want to simplify that, but don't do it. All right, just leave it like this. Now, here's the thing. We have already said that 1 plus 2 plus 3 all the way to k is equal to this. All right, we did that because we just replaced the n with the k from above. That means that this whole section here, 1 plus 2 plus 3 plus k, is equivalent to this guy. So we are just taking him and we are going to substitute. I now have a k times k plus 1 over 2. That's everything 1 through k plus this new part equals this part over here. And again, I know you want to simplify it. Just leave it. All right, you're not supposed to simplify it. And essentially what we're now going to do is we're going to get the left side equal to the right side. So if you look on the right side, you see, oh, this is one common denominator here, so I need to get a common denominator on the right. So I'm going to multiply by 2 over 2. And now I can combine those. I have k plus 1 plus 2, k plus 1. And again, this side over here, you're just going to rewrite it. I know it's a pain. And now we just have to manipulate the left side to make it look like the right side. So one method that we use a lot with mathematical induction is factoring by grouping. So if you notice, you have k times k plus 1 plus 2 times k plus 1. So we're going to just group this. This becomes k plus 2 times k plus 1 over 2. Okay, and again, the other side stays the same. I know you really want to change that to a k plus 2, but we're only supposed to change the one side. Okay, so finally, we can see, oh, well, that's really just k plus 2, right? So we're going to take this k plus 2 and we are going to just split it up. I'm also going to put the k plus 1 first so it looks exactly like the other one. So there's my k plus 2 over 2. There you go. And now that they are equal, we're going to give them a check mark, and then you get to write this really exciting statement, which is since conditions 1 and 2 are met, the statement is true for all natural numbers. Oops, and that is the statement you will write at the end of each one of these. All right, so there you go. That's your first one. So now let's try 4 more. All right, so again, the first thing that we're going to go ahead and do is we are going to do condition 1, which is let n equal 1. All right, so again, you have 2 options for this. You can either just put 1 equals the n squared, okay, and we'll plug in a 1 for n, or you can actually do this guy, 2n minus 1 equals n squared, because again, the whole point is that the 2n minus 1 gets you each of these terms here. So this is just going to be faster. 1 equals, and again, n is 1 squared. So yes, 1 is equal to 1. Notice if you plug in the 1 here as well, 2 times 1 minus 1 equals 1 squared. Oh wow, you still get a 1 equals 1. So do whichever one you prefer. Next, we're going to let n equal k. And this step, we are just literally plugging in a k instead of an n. So we have 1 plus 3 plus 5 plus dot 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 plus 2k minus 1 equals a k squared. All right, and now we are proving true for k plus 1. Okay, so to prove true for k plus 1, your first step is to write this all out, but after your 2k minus 1 term, we're going to do the next term by plugging in a k plus 1. Okay, so it's going to look like this. It's probably easier to write this out than to explain it verbally. So plus dot 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 plus, this is your k term. Okay, this is term k plus your 2k plus 1, or your k plus 1 term is 2 k plus 1 minus 1. All right, so we just took the kth term. I don't think that's an expression, but that's the term k. This is term k plus 1. And we just substituted a k plus 1 in for k. And now on the other side, your k is becoming a k plus 1. All right, so again, the right you're going to leave alone. The left you can go ahead and simplify if you would like. I'm just going to leave it like this for right now though, because the next big step is, you know, that 1 plus 3 plus 5 all the way to 2k minus 1 is equivalent to k squared. So again, this whole part right here, we're just going to replace that with the k squared. And now I'm going to go ahead and distribute over here. This is a 2k plus 2 minus 1 equals, again, k plus 1 squared. And we're just going to keep combining. And you get this. And then this one is really nice because you just look at this and you're like, oh, well, I'm just going to factor it. Okay, just going to factor it, and you do get k plus 1 squared. And so look, they are equivalent. And now I'm going to write my statement. Since conditions 1 and 2 are met, the statement is true for all natural numbers. All right, 2 down, 3 to go. All right, let's take a look at this one. All right, again, first step, we're going to let n equal 1. And we're just going to go 1 equals this side. And we're plugging in a 1. So that's 1 times 1. And oh, wow, yes, it works. Again, you could also plug in the 1 here. 4 times 1 minus 3 is 1, and that would still equal 1. All right, next. Step 2, I'm not sure how much room I have, so I'm going to move this over. We're letting n equal k. And you do have to rewrite this whole thing. But again, all we're doing is replacing the n with the k, or the k. Yes. And everything else is the same. So that is when n is k. And now we're going to prove true for k plus 1. So what that means is this is the term k. We need to do one more term because k plus 1 is 1 after k. All right. Excuse my pen. So we're doing plus 4 k plus 1 minus 3. And we can simplify that, but just don't do it yet. And then on this other side, you are replacing the k with the k plus 1. So k plus 1 to k plus 1 minus 1. That was supposed to be parentheses. That's the side you're not going to simplify. Okay, now, that being said, you can kind of work backwards. You can say like, okay, what would that be? That would be 2k plus 2 minus 1. So really, that whole thing is a 2k minus 1. Sorry, 2k plus 1. And that's kind of helpful to know because we're going to know if we start getting a 2k plus 1 on the other side that we're getting close. So we're just going to kind of leave that like that. Now we're going to do our substitution step. We know that 1 to 4k minus 3, this whole side is equal to this. So let's substitute it in. And now you can go ahead and start simplifying this side. So that's going to be 4k plus 4 minus 3. All right, and again, yes, I know it's a pain to write this whole thing out. That's part of the joy of proofs. You just got to kind of live with it. All right, so let's keep simplifying. Let's go ahead and distribute over here. You can tell that it's going to get factored. All right, so in order to factor, we're going to have to combine all of this stuff anyways. So we're just going to put everything together. Although this is really obnoxious, it is important that you go step by step. Because when you are doing a proof, it's really important that your reader, which is me, can follow each of your steps. Especially since you know what your final answer is going to be, you can't just skip steps. All right, you're not going to get full credit for that. So really do go a step at a time, please. All right, so finally we have this. And what we can do is go ahead and factor that. Now I'm going to have a 2k and a k. All right. And again, you know that it's supposed to look like this. K plus 1 and a 2k plus 1. So let's just try it. 2k plus 1, k plus 1. That would be 2k squared plus 2k plus 1k, which is 3k, plus 1. Wow, it worked. But now we still need to write it out so it looks identical. So what we're going to do is we're going to write the k plus 1 first. And again, you know that 2k plus 1 is this when it was expanded. So now it's okay if you just go to this. All right, but I do need to see this first, and then you can just write it out, and they're equivalent. And just to save time, I'm not going to write out this condition again, but I'm going to say it. Please do write it down. Since conditions 1 and 2 are met, the statement is true for all natural numbers. Okay, this is where your statement should go. Make sure it's there, please. All right, here's another one. If you'd like to try this one yourself, you can go ahead and pause the video, but I'm just going to keep on teaching, okay? Or, you could watch it on 1.5 speed or something. So condition 1, we are letting n equal 1. And so that means, again, we can put when n is 1, be careful here. Your first term is no longer a 1. It's a 3. Okay, so 3 equals, but your n is still a 1. Okay, so this is 3 equals 1 times 1 plus 2. So 3 equals 1 times 3. 3 equals 3. That is correct. Or again, you could just plug in the 1 right here if it, makes you nervous that that's a 3 over there. 2 times 1 plus 1 equals 1. 1 plus 2. And that's still going to give you 3 equals 3. All right, so condition 1 is met. Condition 2. We are letting n equal k. And again, all that means is you are rewriting everything, but instead of an n, you now have a k. All right, and now we are going to prove true for k plus 1. All right, so when we're proving true for k plus 1, again, this is term k. We need to go one more than that. So there's term k plus term k plus 1 is this guy. And over here, we have a k plus 1 instead of a k. Oh, that's a 2. Okay. So now we say, oh, all of this is equal to that. So all of this is going to get replaced. And I'm going to start distributing over here. 2k plus 2 plus 1. And again, this is really a k plus 3, even though we're not going to write it like that. But that way, when we get a k plus 3, we know we're on the right track. All right, we're just going to keep distributing here. And combine. My hand hurts. And finally, we're going to factor, and this factors to k plus 1, k plus 3. And finally, oh my gosh, k plus 3 can be broken apart like that. And voila. Okay, again, you're going to write, since conditions 1 and 2 are met, the statement is true for all natural numbers. Okay, and that brings us to our final problem, which is over here. Okay, this one's a little tricky because you're dealing with an exponential. People tend to not like this one quite as much as the ones that factor, so we'll go through this one a little bit slower. But the start, again, is going to be the same. So we are letting n equal 1. And again, you can either set the first term equal to this and plug in a 1 for n, which is 1/2. 3 minus 1 is 2, and so 1 is equal to 1. Or you can go ahead and set this equal to that. And again, 1 is your n value. So 3 to the 0 power equals 1/2 times 2, and 3 to the 0 power is 1. All right, so 1 is equal to 1. Okay, so next we're going to let n equal k. All right, so let's go ahead, let's plug k in. So this is 3 to the k minus 1 equals 1/2, 3 to the k minus 1. And then, of course, we are proving true for k plus 1. All right, so again, this is term k. We need to do one more term. Okay, so there's term k plus term k plus 1. So k is becoming k plus 1. And it's also becoming k plus 1 over here. Okay, and now we say, oh, well, all of this was just that, so we're going to replace it. Substitute. And this becomes k plus 1 minus 1 is just 3 to the k. All right. Oh, I guess I should write all this down over here. So this is where we're just going to do a bit of algebra, but people don't like how it looks because you're dealing with an exponential expression. Okay. So first thing I'm going to do is I'm going to distribute 1/2 times 3 to the k is not 3/2. Okay. Because order of operations say that exponents come before multiplication. You can't just multiply this 1 times this 3, or 1/2 times this 3. So we're just going to write it like this. 1/2 times 1 is 1/2. Okay, so now I want you to think of your 3 to the k's as x's. Just pretend they're like a big old x, okay? This would be like saying 1/2 x plus 1x. These are like terms, so I can combine them. 1/2 x plus 1/2, or 1/2 x plus 1x is 3/2 x. So I'm going to do the exact same thing here. My x in this case is 3 to the k. So 1/2 3 to the k plus 1 3 to the k is 3/2 3 to the k minus 1/2. Okay, yes, you can do that. That is not illegal. And now you can see that we can actually pull out a 1/2 from both of these. The other reason I'm going to do that is because I know there's a 1/2 pulled out over here. So that kind of leads me in the direction I'm going to go. And this is 3 times 3 to the k minus 1. And we're so close. The last thing you need to do is use your law of exponents here. 3 is really 3 to the first times 3 to the k, and we should know that in this situation we add our exponents. So this becomes the 3 to the k plus 1. And that is that. Check. And for this last one, I'll write my condition, or my statement. Since conditions 1 and 2 are met, the statement is true for all natural numbers. Apparently my pen does not want to write the statement, but it is true for all natural numbers. And there you go. So that's mathematical induction. I hope that was super thrilling and exciting for you, and I hope you have a great day. Bye-bye.